Okay, so in this video clip, we're going to take a look again at the trinomial model and set up our estimation and static code in C++. And we'll compare that against dynamic code also in C++. And in addition, we then will use static code built in with the adaptive mesh model, which was proposed by Figuritsky and Gao in 1999. And this adding in a finer mesh in the trinomial substrate does improve the accuracy of the model. It also adds, because of the extra nodes here between the ultimate and penultimate set of nodes, a little bit more time is consumed, but we will use boost libraries in the code. And again, that's provided by Fabrice Roy. And then we again implement adaptive mesh model, but this time without boost libraries. Okay, so we'll do the same again, and we use vector instead of the matrix command that we have in this code here, and just make some time comparisons then. Okay, so to run, basically, we're going to take the values provided by Brody to Temple 1996 as yielding a measure of true. So we're going to take an American call option, and we're going to set out our case where the stock price is 100, the exercise is 100. We're going to take the risk-free rate is 3%, the dividend yield is 7, the volatility on the asset price return is 20%, and the maturity here is given as 3 years. So with those parameters, we can estimate using the trinomial model the value of an American call. Now we know true here is given as 9.066, so we're going to accept that as true, even though this is a binomial estimation. It's coming at 15,000 steps. So it is quite accurate, and we will take this as true. And with the first snippet of code, again, the difference between binomial and trinomial is the trinomial introduces 2 tree branches extending from each node going from left to right, whereas the binomial would only incorporate 2. So we get an extra, then mesh is just naturally more dense with the trinomial model. Now, when we run, again, this code comes from Fabrice Roy, and it's static code. I've done this in a previous video clip. But just to note, we're going to take the same parameters as suggested by Brody and the Temple. And then we're not going to go with 15,000 steps. We're going to go with 1,000 steps. We run that in Google Colab using C++. Note that we just have to prefix the cell with double percentage sign write file main.cpp, and then to output the result there, script bash, and we get an estimate of 9.044 and in 0.22138 seconds. Now we can compare that against what's in what we have from Brody to Temple. It's relatively close, 9.0644, 9.056. Okay, so it looks quite close. Okay, let's go again, come down, this time move from static to dynamic code. And we did this based on Hogue, Espen Hogue VBA code, and we set up the trinomial again to replicate Hogue's implementation in VBA, and we set this up in C++. And when we execute that code and output using script bash, you can see we get a small speed improvement, but we get exactly the same results. So as anticipated, using just the basic trinomial model, the result is coming in as before compared to the static model, so 9.0644. Okay, so that's great. But we do get an improvement in in the time it takes. So 0.22138 seconds here with the static, and with the dynamic code we improved that to 0.107374. Otherwise exactly the same, but there is a speed improvement. Okay, now with our adaptive mesh model, we would expect that there would be an improvement in accuracy, but because of the extra nodes incorporated in going between the ultimate set of nodes and penultimate, this would take more computational time. And in the first snippet of code, we're going to go exactly with what was provided by Fabrice Roy, and we're going to, in this time, instead of using vector, we're going to use the boost libraries, and we'll run that snippet of C++ code. But just for you to note, there is a difference here in the modus operandi, and that is we're using boost libraries, right? And that then means that we then use matrix instead of vector. And let's output our results here. And again, it's the same set of parameters as before with 1,000 steps. It's a call option and it's an numeric option. And when we look at results here, it's 9.063. So again, to compare against the previous snippets of code, it looks to be more accurate, right? So 9.63 as opposed to 9.64. And it compares favorably with the true value. Slightly unbelievable though is the time period taken is a negative time period. So there may be issues around the turbo or the boost libraries here look a little bit incredulous, and I don't have an explanation. I did read a link. I think I've shared that link with relating to the boost libraries, and it is a little bit too good to be true. So we are getting a negative time reading, and unless we have a time machine, right, that's a bit counterintuitive, but there seems to be a speed improvement if we were to take this as credible. And of course, then that does lead to a question mark. Okay, if we use the AMM model with the same static approach without boost libraries, so in every respect comparable to the first approach with the static code we had used initially, except we do include in this finer mesh in the substrate of the lattice, right? But we do it using the approach that we had initially used. That the output then from that AMM model is the same as, should be the same as what we've just estimated. So it makes no difference in terms of accuracy. The 9.63759.372 is the same as what we obtained with the boost libraries, right? But the time period is, of course, it's higher. And it's higher compared to the original static library, right? 9.644, here we have 9.063, and the true value is 9.056. So it has improved, but then we slow down, okay? And so we can see that AMM has introduced an improvement in terms of accuracy, but to compare directly with the other trinomial, the static trinomial that we introduced, the first segment of code, it is a little bit slower with a little bit higher accuracy. So there is that trade-off between the two. You get higher accuracy, but there is evidently it takes longer, except if we use the boost libraries, then we get a reading for time speed, which is better. But because it's negative, we have to raise question marks in terms of, is it how credible the results are. Okay, I'm going to leave it there.